Am I audible?
Yes, sir.
Thank you. So in this session, we have phase plane analysis. The first topic is phase plane analysis. Second is Sturm comparison theorems, and third is the um, initial value problems. General, non-linear ODEs. Okay, entire these three topics are on ODEs. No more now PDEs. All the ODE stuff will be here. So the main problem is to do the yeah. First is let me just give a brief introduction about these three topics. What is phase plane analysis? What is Sturm comparison theorems, and a overall picture. So please let me know if I am not audible or not connected. Okay. If you cannot see the notes, please let me know immediately. Send me a WhatsApp. So let us consider a second order equation. Del square x upon del t square plus some p times del x upon del t plus q times x is equal to 0. The second order ODE. So if we can write this we can always write this as minus p dx upon dt minus qx. So x is now the unknown function. X is a function of t, and we have in the right hand side, what we have in the right hand side is a function of x and dx upon dt. So if here basically if I can do a substitution, put dx by dt is equal to y, then d square x upon dt square is equal to dy upon dt. So what we can write is we can write our differential equation as dx by dt is equal to y, and dy by dt is equal to d square x by dt. This is f xy. So this is f xy. So we can write the given second order differential equation as a system of a system. Call this as f1 xy and f2 xy. Okay. So nowhere now in the right hand side here the t is not emphasized. The t is underlying t is now ignored. Now we have only the system of ODEs, um, system of ODEs and first order. Now we reduce into first order. First order system of ODEs. And what is now phase plane? What is now x is x and y are the actual. What is x? X is the state of the system, and y is what? Y is dx by dt. So this is the velocity of the system. So or phase, what phase it is, phase of the system. So that's why the state variable is x and phase variable is y, and that is we are looking at the x and y, and any and we have uh, we are working on, and what is the final thing? Final thing is the d square x by dt square. This is the acceleration. So instead of studying this thing, we are now studying. So any point in the plane, xy plane, what is any point x naught and y naught, and if we take any curve passing through this x naught y naught, it will give us any curve in the xy plane gives us the solution, gives us um, the solution xy. Okay, of the system. We look at various examples, but just we are introducing what is phase plane analysis, or yeah, what is this? How we are converting given a second order differential equation into a system of first order equations. Okay. And now um, instead of now solving the second order equations, we will look at only the first order system. Various examples we will look at. Examples of such systems, the motion of simple pendulum. It is given by d square x upon dt square is equal to minus c upon a sine x. Okay. Here a is the all these constants. These are constants. A and c are constants, and x is the um, motion, and the acceleration is given like this. And suppose we have again a damping factor that is given by dx by dt. And for small oscillations, we can approximate because sin x series is x cube upon 3 factorial and so on. If you just put x as the approximation for sin x, then we have for small oscillations, then we have a simple pendulum equation like this, and we can write c upon ax, and here some other upon m and q upon epsilon. Okay, now this is a right hand side is a function of x and dx upon dt, and now if we make this substitution as this is equal to y, we'll have a system. So there are other examples. This is example 1. Example 2 is Van der Pol equation, and so on. All these details are given in the notes. So we have as the first topic all these phase plane analysis. Okay. Next we have, we'll come into the details in the coming classes. So next is Sturm's comparison theorems. So these are comparing the solutions of, like, if we have a differential again second order differential equation, dt square plus p times dx upon dt plus q times dy upon q times x is equal to 0. So here we will first do the equivalent thing, that is, instead of having this all three terms, we can ignore this term. We can have something like d square y upon dt square plus some other time y is equal to 0. This is called normal form. Instead of working with this differential equation, we can get rid of this dx by dt term and get an equation, another equation, which is of this time, where here we will have a function of p and q. So we can work, instead of writing the Sturm's theorems for this thing, we can do the analysis for this. This is called normal form. Okay, given this sort of second order equation, we can reduce to a normal form by basically it requires a substitution. Okay, change of variable, etc. We'll go to details of that later on. After reducing the normal form, we can compare. Now comparison, instead of so we have y double prime is plus y is equal to plus some q of x y is equal to 0, and another equation y double prime plus q1 and q2 x y is equal to 0. So if q1 is greater than q2 and positive, what can you say about the solutions of this oscillations of solutions? What are called, what are oscillations? Oscillations are nothing but the zeros. Oscillations are nothing but, suppose y1 or phi is a solution of this, phi of x is solution of this, and psi of x is a solution of this. What is meant by oscillations of the solutions? It can happen that there is no oscillation, or there may be one oscillation, two oscillations, or infinitely many oscillations. Oscillations means what? The zeros. So the question is now, phi x has no zeros or a finite number of zeros, finite number of zeros, or infinitely many zeros. Without solving the differential equations, we will study only the oscillations or zeros of the solutions. Okay. So if q is bigger than q1 is bigger than q2, what can you say? If what can you say about the oscillations of psi x, and what can you say the oscillations of psi? Comparing the oscillation, comparing the zeros, okay, of q1 and q2. That is the question here. So these are called Sturm's theorems, and final topic is, so what are the applications of Sturm's theorems? Applications of some complicated equations, differential equations, can be compared with equations like this, like 4y is equal to 0. We know the solutions of this. We know that cos 2x, sine 2x, or these are the solutions of this sort of equations, right? We know that. So if we have a differential equation where the q term, if we have differential equations where the q term is complicated, and we can compare with qx is greater than this 4, then what will happen is the zeros of this will lie in between the zeros of. So suppose cos 2x has zeros like this, here, and so on. Then in between every zero of the solutions of this, will have a zero of the solution of this complicated differential equation. That is the application of Sturm's theorems. We can compare without solving. We don't have to solve. Sometimes it is not possible to solve the complicated differential equations, but at least we can have an idea of the zeros. When we know the zeros, then we can understand. Okay, it is now above the x-axis or below the x-axis. We can understand. So at least we can have an idea about the zeros of the solutions, oscillations of the solutions. Okay, this is application of Sturm's comparison theorems. Then finally comes the general nonlinear ODE. The first, you have already studied equations like that. Dy by dx is equal to f of xy, a single equation. Okay, here f is a nonlinear function, and we have studied something called Picard's theorem in the course MTL 101. Okay. We have studied how to solve. There is something called successive approximation approximation method, or Picard's method. What are successive? We know that if we have an initial value problem like this, with this problem with an initial condition at x naught is y naught. Okay, this initial problem is equivalent to solving an integral equation. Y of x is equal to y naught plus integral x to x naught to x f of t y of t dt. Okay, this problem of solving initial value problem is equivalent to solving an integral equation like this. So we have an unknown here also, we have an unknown here also. Okay, so this is an integral equation, and f is non-linear. Okay, so these what are the approximations here? Let us first we can take phi 0 as y0. Phi 0 x is equal to y0 itself. Start. This is the first iteration. We are doing a successive approximation, and these are the approximate solutions. Iteration, first iteration or 0th level. Then phi 1 of x, define phi 1 of x as phi naught x, or we can call it as y naught plus integral x naught to x f of t phi 0 t dt. Okay, this is phi 1, and this is the second iteration, and so on. Now phi 2 of x is equal to y0 plus x0 to x t phi 1 t dt. We are just recalling already what we have studied. This is the third iteration, or the first approximation, second approximation, third approximation, and so on. And we have finally, in general, I plus 1th approximation is equal to integral x naught to x f t I phi t dt. Okay, this is I plus 1th approximation. Now the question is, will these phi n's converge? Okay, now converge to what? Converge to, if they converge and converge to phi, then phi is also a solution of this integral equation. And finally, our solution, solution of the so these are the partial sums. So we know that convergence of partial sums is equivalent to partial sums of what? Phi n, phi n's are for partial sums, because um, yeah, uh, yeah, sequence of partial sums convergence is equivalent to convergence of the series. Convergence of the series. Okay. So how to write the partial sums and so on? All these convergence, everything we have studied, and um, this is the scalar case. Now the question is, and what are the conditions on f? F should be continuous. F is continuous function. Whether it is f is a function of x and y now. X, y. So is it a rectangle, finite domain, or infinite domain? Is it a strip? F is continuity is given on a strip, infinite strip. X is minus alpha to minus beta, my alpha to beta, and so on. Y is anything infinity, minus infinity to infinity. So this is an infinite strip, this is a rectangle, and so on. And continuity, is it given here or here? And we also need something called Lipschitz continuous. Lipschitz continuous. F of xy, is it Lipschitz continuous? If these are again Lipschitz continuous on a rectangle or on an infinite strip, accordingly we will have the solution. Local solution, non-local solution, local existence, non-local existence of the solution. These are the conditions on the given F, continuity or Lipschitz continuity. So now the question is, what is the vector case? That is, if we are given instead of F, we are given a system of equations now. dy1 upon dx is equal to f1 x y1 y2 so on yn. dy2 upon dx is equal to f2 x y1 yn and so on. dyn upon dx is equal to fn x y1 so on yn. So these are system of n coupled non-linear ODEs. Okay, and first order system non-linear ODEs. That is f1, f2, fn's are non-linear functions, and these are vector functions. f1, fn are defined on R or C, Cn. This may be R cross Cn. Okay. These are vector functions, and now I can write it as let us write this as capital F. So we have fy dx dy dx is equal to f bar. Now y bar and f bar. Okay. F bar is equal to f1, f2, so on fn, and y bar is equal to y1, y2, so on yn. Dash is equal to this. So instead of a single equation, we have now a vector equation, first order. And so what are the conditions? What do you mean by f bar continuous? Is equivalent to each fi's continuous, and these are vector functions. So what is the meaning of continuity here, and what is the meaning, and what is f bar Lipschitz is equivalent to, how it is equivalent to fi's Lipschitz, and so on. What is the corresponding Picard's theorem successive approximations? How do you define the successive approximations here? Earlier we defined what is the integration now, x naught to x f bar t y bar or y bar t, okay, dt. So is it just integration of individual functions? Yes, it is. T y bar t dt x naught to x and so on. Fn t y bar t dt x naught to x. So then we can define something called y is equal to our solution. Our solution y. So all these things, details, we have to work it out. that exactly the scalar case can be generalized to the vector case, and we can define all these things. And also, okay, this is the scalar case, and here also we yeah. So this is another topic. So now these are actually solving exactly, so solving the equations, but the phase plane analysis and the terms are qualitative theory. This is quantitative, and this is qualitative. Phase plane analysis and terms Sturm's theorems. Okay, qualitative means what? We don't exactly solve the equations, but we study the nature of solutions or behavior of the solutions, behavior, nature or behavior of solutions without solving the ODEs. So main thing in the phase pair analysis is there are something called critical points. Like if we have the system xy dash is equal to f and g, fxy and gxy. This is called autonomous system, and depending on the f and g. The f and g are twice are continuous functions, and also um, partial derivatives are continuous. That is del f, del x, del f, del y, del g, del x, del g, del y exist and are also continuous functions. These partial derivatives are continuous. So these are like something like f and g are continuously differentiable functions, vector functions, and what is meant by when derivative of f with respect to x at the point is equal to 0, and derivative of uh, yeah, when they are equal to derivative of g also equal to 0. What are these called? The points where these derivatives are 0 are called critical points. Sorry, no. What are where f x naught y naught g x naught y naught, if they are 0, then x prime at x naught y naught and y prime at x naught y naught is equal to 0. This implies x naught y naught is a critical point of the system. Critical point of what? Actually, this xt and yt are the functions, and x prime t, yeah, x prime and xt yt are the actual functions. So the points where f is 0 and g is 0, that means x prime is 0, y prime is 0, are called critical points, and these denote the critical points are the points where the system has a steady state or equilibrium. System is equilibrium state. Why? Because y prime. What is x prime? X prime at x naught y naught is equal to 0 implies that what is x prime? X prime is y. Y at x naught naught is equal to 0. That means there is no velocity. Where y is the velocity. The velocity is 0. And y prime is what? D square x by dt square. So the y prime is 0 implies no acceleration is 0. Acceleration is 0. That means there is no velocity, 0 velocity, 0 acceleration. That means it has attained a steady state, that is equilibrium state. There is no change in the system, so equilibrium state. And the critical points where these x prime is equal to 0 and y prime is equal to 0 are called equilibrium state. Okay. Now uh, now once we have introduced what is a critical point, what is the nature of critical points? Nature of critical points. So there are something called the nature will be like they are centers, sometimes they are spirals, sometimes they are saddle points, and they are called sometimes nodes. These are the four types of critical points. These are all we'll study in detail. When do you call a critical point? For example, if you have dx by dt is equal to y, and dy by dt is equal to x. Do we have such a system? Suppose this y double prime plus y is equal to 0. What is the putting now? Or yeah. So x double prime plus x is equal to 0. So put x prime is equal to y. So we have x prime is equal to y. So this is first equation. And x double prime is equal to y prime. Y prime is equal to what? Minus x. So this is minus x. So we can change such an equation into a system like this. Minus x, y prime. So this system, if we have, what are the critical points here? This is our right hand side function f. This is our g. So f is equal to g, and also equal to g is also z. What is the point here? That means points where f and g are both 0. That is x is equal to 0 y is equal to 0. That is origin. Origin is critical point. So when origin is a critical point here, so we can have solutions like if origin is the critical point, we have solutions like, for example, periodic solutions are like this. Periodic solutions, they are, the paths are, these are the paths or trajectories, that is xt yt, xt yt. These are the points. What are the xt yt? This is cos t sin t, right? Cos t sin t are the solution. So cosine t and sin. So as t, cosine t and sin t, we can represent them as circles, and so the paths can be centering the critical point. That is the first case. Centers, critical points are centered. Then we can have the second thing, that we can have the critical point if the origin is there and it can be spiraled, or the spiral. This is the second case, spiral. And third case is saddle point. That is the paths are like asymptotic. And finally, fourth one, this is a saddle point. I am drawing only one curve like this. There may be many paths, but none of them will touch the point origin. Here also they won't touch, they will just spiral. Okay. And fourth is something called nodes. These are the critical point where they will enter, pass through. Okay. Nodes. So we will study various examples where the critical points are either nodes or saddle points or centers or spirals. Okay. Then finally, why we do the analysis for linear cases and make conclusions or compare the nonlinear things, nonlinear ODEs with linear uh, behavior, linear cases, linear ODE cases. Okay. So this is the final application of this phase plane analysis. Phase plane analysis application is to compare the nonlinear ODE situations where we cannot solve the system of ODEs, but we can solve the linear systems. For example, this is a linear system, dx by x y whole dash is equal to y minus x. This is a linear system. These are linear functions. And compare this with any non-linear, like if it is sine x or exponential x in the right hand side. These are non-linear situations. So this is the objective of phase plane analysis. Phase plane analysis also we have to not only the nature, behavior, nodes and these things, but we have also called something called stability. Stability of critical points is equivalent to the stability of nonlinear systems. Okay. Stability of critical points is equivalent to the stability of nonlinear systems of equations of ODEs, and there is also called Lyapunov stability. Stability analysis after this. Okay. So this is the overall picture of what we are going to have for the next few classes, and yeah. Another thing is why we are calling this as qualitative analysis. Qualitative is we will study only the behavior without solving. For example, you consider this equation y double prime is equal to y double prime plus y is equal to 0. This initial value problem. Y, let us take y at 0. Y at 0 is equal to 0, and y prime at 0 is equal to 1. Or you can take same equation y double prime plus y is equal to 0. Y of 0 is equal to 1. Also you can take y prime at 0 is equal to 0. The simplest examples, if you take either this or this, and what is going on here is without we know the solution. Suppose just pretend that you don't know the solution of this system, this initial value problem. Okay. So what is here? What is let us say y1 x is a solution. Now we can study the behavior of y1. Y1 of 0, because this is a solution of this equation. Y1 of 0 is 0, and y1 prime of 0 at 0 is 1. What does this say? That is y1 is a function which starts at origin, it is 0 value, starts at origin. And what does this say? Y1 dash is the slope of the function. Slope of the function at 0, at the starting point, slope is 1. Okay. It has something positive slope, and it is going in this direction. The slope, the function is now we don't know the behavior of the function, but we know at this point it is 0, so starting at the origin, and slope is positive, slope is 1. And now come to the equation y double prime is equal to minus y. That means y1 double prime is minus y1. Okay. So this implies y1 dash slopes variation is negative. So starting y1 at 0 is positive, so this is negative. So slope, what happens to the behavior of the slope? Variation of the slope is decreasing. Variation of the slope is decreasing. That is, as this goes further, it will slope will decrease. And at some point, the slope becomes 0. And later on, it keeps on decreasing, and at some point it becomes the function value again becomes 0. And if you continue the analysis like this, you can see that again it is increasing, and it will become. So this is and you can do the same thing this side also. So from this we can conclude that sin x is a possible solution. We can even conclude without solving that the periodicity also we can conclude that whatever this and these points, this should be pi, this should be pi by 2, and so on. So this is a function which is periodic, and it is sin x. And if you take this initial data, you will get cosine x. So without actually knowing the solution, we can study the behavior of the solution. That is why it is called qualitative theory. So all this is in detail given in the notes. Please go through. And are we connected?
Yes, sir, we are connected.
Yeah. So this is the overall picture. We'll go in detail and solve the exercise problems also. So only thing is here we have three different topics. Sturm's theorems are there, phase plane analysis is there, and another the scalars, the vector first order system is there. Okay, please go through all these things, and we'll continue in the next class with more details. Okay, we'll stop here. Any more any queries?